Hi, this is Bob, W9RAN, and this is my presentation on the Pico Rx, a software-defined radio receiver anyone can build. This presentation was first given at the W9DYV Technical Symposium, which was held January 17, 2025. The W9DYV Technical Symposium recognizes the contributions to the radio art of Westsham W9DYV and his company Central Electronics, an innovator and leader in early single sideband. The goal of the symposium is to inspire others to carry on his tradition of experimenting, homebrewing, and technical innovation. In a way, this is a story of two young boys. On the left is me, who grew up in the 1950s in the middle of the U.S., and as you can see, is enjoying a Remco crystal radio. The other boy is named Jonathan Dawson. He grew up in the 1980s and had a Radio Shack crystal radio in the United Kingdom. Now there's a connecting point between these two. When I read this statement, I found that we had a lot in common. In fact, I could have written what John wrote on his Pico Rx project website. To start with, let's just take a quick look at receiving technology and how it's changed. Starting in the late 19th century, the development of devices to receive radio signals evolved quite rapidly, thanks in large part to the genius of Edwin Armstrong, who first brought us regeneration and then the super heterodyne receiver. That all happened in about 20 years. And for the next 80 to 100 years, receiving technology pretty much stayed with the superhet. Until the early part of this century, when we started to really see software-defined radio becoming affordable and widespread. A major factor was the Taylor detector, which I will refer to as the Quadrature sampling decoder, which was patented in 1998. That gave rise to the soft rock kits and actually to flex radio. But again, in about 20 years, the technology had advanced to the point where we had commercially available direct up and down conversion transceivers like the ICOM 7300, the homebrew open source Hermes Lite, and even the little micro SDX, which was able to extract performance from an 8-bit microcontroller. So it might seem strange if I were to tell you that the next big breakthrough in software-defined radio isn't a radio at all, but a microcontroller. The Raspberry Pi Pico microcontroller, which was introduced in the early 2022 timeframe. It's got a dual Cortex M0 processor and can run quite quickly at 133 megahertz clock speed. It's got a lot of memory, supports USB, can have a number of features, most particularly a very easy to use drag and drop programming method that makes it look like a memory device over USB. It's got a lot of GPIO and quite a few useful peripherals, including 2 I2C, 2 SPI, 2 UARTs, and a lot of PWM as well as A to D channels. It's got an accurate clock, and it also has a temp sensor and accelerated floating point on chip. But most interestingly, it has something called a PIO, or a programmable I/O device. Let's take a little closer look at that. But before we do, it's important to note this microcontroller only costs $4, and it's capable of doing things like SDR. So what is this PIO? Well, it's a piece of programmable hardware that includes up to 4 state machines that can independently execute small programs. Now, why would they do a thing like that? Well, because even the smartest chip designers don't foresee everything that an application might need. So the PIO gives you this little chunk of programmable logic that you can execute high-speed digital control with independently of the main CPU cores. So this isn't a processor that you write software for as we normally think about it. It does require software, but it runs very fast. In fact, it doesn't even depend on the Cortex microcontroller cores. But it can communicate with them by means of a buffer and interrupts. The programming is done using assembly language and 9 really basic instructions. Here's an example. This set of instructions generates a square wave on a GPIO pin. And if you were to compile and execute that program, as you can see the number 31 up there, it will generate a square wave that has a period of 32 clock cycles. Or at normal clock speeds, that's 1.953 megahertz. And you can even do much more complicated waveforms than that. But let's stop for a minute. That's an HF range RF signal being generated by a microcontroller without even using its CPUs. That's what makes the Pico really special when it comes to SDR. A fellow noticed that named John Dawson, and as part of his 101 Things collection of projects, developed a Pico Rx. This became public about a year ago in late 2023, and it has some really interesting features. Among them, he claimed that it could cover 0 to 30 megahertz and could receive CW, SSB, AM, and FM. As you can see, it's got a built-in display with a spectrum scope. It could play back through headphones or a speaker, and it had some interesting things like 500 memories and could run on batteries with very low current consumption. It incorporated a number of innovative features. For one, it was using the Pi microcontroller to directly generate the quadrature clocks needed to drive the quadrature sampling detector. Now, this had never been possible before, and only the Pico could do it because of its unique high-speed PIO. It implemented a low IF design, which reduces the noise and improves intelligibility of signals. It had a time domain-based DSP, which was well documented for learning, and it even included a preamp, so you could use an inefficient antenna and actually hear some signals. Well, I had to build it, and this is my version on the left without the top board attached. I found a few things that were of concern, however, and they included birdies, unwanted signals where they shouldn't be. I also heard aliases, false signals, for instance, CW signals in the single sideband part of the 20-meter band was a common occurrence. As you went higher in frequency, it seemed that the image suppression disappeared. That is, you would hear muffled lower sideband signals when listening to upper sideband, and the signals were not as pure and clear as they ought to be. The audio turned out to be too weak for a speaker. That was pretty easily fixable. It did have an awful lot of surface mount parts, including a filter and an expensive little op amp for the preamp, which made it kind of difficult to troubleshoot and modify. And overall, I was thrilled to play with it, but felt it's time for me to step up and make my own version that I could play with. So here's what that looked like. I kind of divided the problem up and made 2 printed circuit boards. The small one on the left is the QSD board, It includes the TALO detector and just a few jumper connections to pick up the needed control signals. And it had an audio output jack, which I could either use with a PC to characterize it, or it could just be plugged into the mating jack on the right-hand board, which had the Pico on the backside, the OLED encoder, and the human interface. I left off the preamp and filters because I was aiming to understand how it worked and felt they should be something I could add later as needed. What was learned by this was really significant because even in my previous experiments with the QSD, I ran into problems with image suppression. And now we had this new problem of the image suppression becoming worse at higher frequencies. So what's going on here? Well, what we found is that the op amps would be driven into saturation, a thing that happened more prominently as you increased the frequency. And once the op amp's output hit the supply rail, there was no longer any I or Q output from that signal. Therefore, the DSP couldn't work right and cancel the image. Well, the root cause was found to be small DC offsets and component differences that did become more pronounced at high frequencies. The solution was to add DC isolation capacitors on the inverting inputs of the op amps. Credit for this goes to Guido, PE1NNZ, who did the same on the true SDX. So now that we had the Quadrature sampling detector under control and the QSD could work as it was supposed to, it worked a lot better. Let me show you a little bit of a graphic that John created that helps to explain how the QSD actually works. So on the left in purple is the RF input signal, and at the bottom coming in yellow is our PIO based Quadrature clock. What happens in this 4-to-1 analog switch, which by the way was designed to switch digital signals, nothing to do with radio or RF, but it operates 4 times for every single cycle of the Quadrature clock. So basically we're taking 4 little snapshots or subsamples of the RF with every cycle. And those snapshots are held in what you might call a sample and hold, which is in fact a low-pass filter, and then they're amplified. So taking it from left to right, the analog switch samples the RF every 90 degrees or 4 times per cycle. The sample voltages are held in a capacitor, which acts as a low-pass filter. And since half of them are redundant because it's a sine wave, we can differentially amplify and combine them in an op amp. Now this detector or demodulator has very high efficiency because the only source of loss is the resistance of the switch, which is only about 9/10 of a decibel. And we get all of our gain in a low noise op amp, and that's about a gain of 500 to 600 times. And with the series capacitors, we realize all that gain without reaching saturation. This gives us a minimum sensitivity, that a minimum discernible signal of around 120 dBm, minus 120 dPm, which is very good. That's a fraction of a microvolt. And it gives us the I and Q output needed so the DSP can do its thing. Let's talk a little bit about that free tracking filter that TALO mentions. If you take a look at the small diagram or blown up on the left, you see it's an RC circuit. Now the R is really all of our antenna circuit impedance and the resistance of the switch. The sample capacitor forms the C. So we can very simply adjust those capacitor values to tune this detector to any desired bandwidth. And in the Pico Rx, our capacitors are designed to give us about a 12 kilohertz, very narrow bandwidth. And we carry that over through the choice of cutoff capacitors in the op amp, because as an active amplifier, we can tailor its response. The last thing that we did was to add a 12 kilohertz low-pass filter on the output as an anti-aliasing filter. Now that's necessary in the Pico Rx, even though you don't see it on many others, because the Pico is actually sampling at 250 kilohertz, whereas most QSD receivers sample basically at audio. So we're knocking out anything that might show up as an alias by an additional 30 dB. This graphic shows all of the above in one animated view. At the top, you see the 4 color-coded subsamples of the RF signal. In the middle, they're spread out in quadrature, or every 90 degrees. And at the bottom, you see the filtered output from the op-amp, which has basically recovered the thing we're interested in, which is the signal itself, the modulation of the signal. Now that DSP inside the Pico Rx has undergone a major change. The diagram that I'm showing is the way it is today, but initially the first generation used time domain processing, which is a common method. It's what in the amateur radio world we would call the filter method, because it reduced the sample size and then used a digital filter to slice off the unwanted sideband. It worked fine, but it was requiring 80% of those Cortex M0 CPUs. So we were pretty much out of CPU power. But thanks to the great work of the Raspberry Pi Foundation, the Pico 2 was introduced last year, and it contained more powerful Cortex M33 CPU cores, as well as RISC-V cores. The upshot of that is the increased CPU power in the RP2350 microcontroller reduced the CPU load required by the Pico Rx by about half. So with half of the CPU now available, John was able to recode and implement FFT-based DSP, all of which bodes very well for the future of Pico-based SDR. Let's take a real simple look at the FFT-based demodulation. Everybody knows now who's sat in front of an SDR receiver what the time domain and the frequency domain look like. So as we look at our frequencies, left and right of a center, the first thing that happens in the Pico Rx is we use the fast Fourier transform, or FFT, to convert our IQ signals out of the QSD from time to frequency domain. We spread them out pretty much into bins, just like you see here. Each bin is kind of the output of a narrow pass filter, a very little sliver of the spectrum that we're bringing in. Each bin has its own phase and magnitude value, representative of the sample at that particular frequency. So it's really a lot like internally the modern transceivers spectrum display externally. Now in the end, what you accomplish with DSP is the same, whether it's done in the time domain or the frequency domain, but less than 256 bins is a little more efficient in the time domain. However, the frequency domain has some neat advantages, and that's why we use it. In the Pico 2, 256 bins give us the equivalent of a 256 tap FIR filter, and the bandwidth equivalent of 117 hertz per bin, which means that our filtering is pretty simple, because all we have to do is figure out where, say, the upper sideband is, keep those bins, and delete everything else. And that's exactly how it's done. We can also do neat things like automatic notch filtering and a waterfall display are simplified when you already have the FFT in memory. The last thing, of course, we have to use the inverse FFT to convert the result back to time domain audio so we can hear it. This graphic shows the windowed overlap method that is used. It involves dividing the input signal into smaller overlapping segments, applying filter in the frequency domain to each segment, and then recombining the segments to get that final filtered signal. Now, I'm not the guy who's going to implement FFT-based DSP, but I thought I could contribute to the project and made my own list of goals that I wanted to accomplish in my next iteration. So the first thing is I felt the Pico Rx code was really outstanding, and maybe I could provide a good hardware platform that would make it easier for folks to build it and to take advantage of it and enjoy using it. I wanted to make it as easy as possible for all builders, so that really meant all through-hole components, or as close thereto as I could come. I do like minimalist design, that is getting usable performance. In this case, it meant the complexity of the front-end filters, which involves a bank of bandpass and low-pass filters, adding 20 to 30 surface mount components, was going to be dispensed with for the time being. I wanted to see how good could a receiver be made without front-end filtering, just using the tracking filtering of the QSD. I wanted to make sure and use readily available and inexpensive components, again, to lower the barrier to entry and make this a fun project to build. I wanted to have good loudspeaker audio, and I wanted some flexibility in the power sources, so you could use batteries if you wanted to, but maybe USB power and other sources, AC and DC, would be good. I wanted to put it in a cabinet that had an attractive appearance and have some fun with packaging. And mainly, I wanted to really do something that would motivate others to dive in and experiment on their own. There's a reason this sounds familiar to me, and that is my reference point for shortwave radio goes back to age 11 and a Night Kit Span Master that was under the Christmas tree in about 1962. My dad and I put it together in 2 nights. It's definitely a minimalist design, but still a bit of a challenge for a newcomer, and to my great surprise and pleasure, it worked right off the bat. I thought it was a great looking piece of equipment. It had a built-in loudspeaker, so you didn't have to wear ear-crunching headphones. And sure, its performance wasn't great, and it took a pretty delicate touch to tune in weak signals and to keep them tuned in, because it is, after all, a regenerative receiver. But it was great fun. It started me on my ham career and also on my professional career path. So I'd done this before, and I wanted to do it again. Here's the PC board I came up with that I call the Simple Pico Rx. There's the Pico in the middle, kind of arranged in an L shape around the right-hand side is the QSD, and you'll notice that there is a surface mount part. Well, that's because the 3253 4-input multiplexer is only available in surface mount. But I'll show you a workaround for that in just a minute. I brought in USB power from a USB-B mini jack because that's the smallest USB connector you can hand solder. And I went to the internet for a Class D audio amplifier that you can buy for about $1 and gives nice quality audio in a very small package, in a Class D amplifier. And up front we have the tuning, and I put on a hardware volume control because I just wanted to be able to turn the volume up and down without using software. So that's my Pico Rx. Oh, by the way, I mentioned that workaround. You can buy these SMT to DIP adapters very inexpensively at places like Amazon. If you have a difficulty soldering even an SOT16 package, buy the IC, get a buddy who can do surface mount, have them solder some pin headers on it, and you'll notice the board is set up to accept that. You could even put it in a socket. When you get ready to wire up an antenna, you just need an RCA, no special SMT or anything else. And if you want to use headphones, there's a jack for that. Otherwise, you've got built-in loudspeaker audio. And I guess I'll call it 99% SMT free. Well, here's what I ended up with. My first version was a 3D printed enclosure that kind of was inspired by the Catlin radios of the previous century. You can, of course, make it any color and shape and style you want. I wanted something that was in an upright cabinet and posed a few challenges like the speaker grill and, well, how do you mount those OLED displays anyway? Well, I did another one first and then I solved that problem. This is the low profile version, and I just laid the speaker on its top, same insides otherwise, and a different color scheme. Well, to mount the speaker, you needed to make an enclosure, and I came up with a way of sandwiching it between the grill and the enclosure with a 3D printed speaker grill. And to mount the OLED display, a mounting bezel with a small clip that goes on the back side and a piece of sponge rubber that provides a nice cushion for the back of the display. These are functional parts that can be 3D printed in a matter of maybe 20 minutes. And that's the beauty of 3D printing when it comes to making radios. You can come up with an enclosure of your own design, or you can go find mine if you like on Thingiverse. You can modify things as you need. And I do all my design work with Tinkercad. It's simple and easy. It's fun to use and gets the job done, as you can see. Another way is you can just go to places like Thingiverse and find existing 3D designs that meet your needs. This is the knob. I didn't feel up to trying to come up with a knurled knob. I like the looks of this one. Brought it into Tinkercad, did a few changes to it, and now I can 3D print them in whatever color and size I want. Other changes have been made since I first made my receiver. There's an option for a 7-wire SPI interface to drive the ILI 9341 TFT display. And you can get those displays in various sizes. This display works in parallel with the OLED display. So you can kind of view the OLED as your control panel display and this as the color graphic that shows the waterfall and spectrum and even the S meter. So all you have to do to use it is go into the software and turn it on. Another neat feature that was implemented is USB connectivity. I mentioned that the Pico does support a USB 1.1, and through that it can appear as a complex device in Windows or Linux. That means it shows up as an audio device, a microphone in Windows that you can select as the source of audio for any digital mode software. It also shows up as a serial port that can be chosen to do cat control. It emulates the Kenwood TS480, and you can then go into your digital mode software like WSJ-TX or FLDigi, set that device up as your audio and cat source, and do all the digital mode reception that they make possible. So you see a couple of examples of that below. There's an awful lot of features. I can't go into all of them, but there will be a short video that does so. The memories can store frequency, mode, and even the AGC setting. There's an auto notch filter that will take out heterodynes. You can not only adjust the AGC time, but also its threshold or control it manually. In addition to the normal modes, there's FM and AM with synchronous detection. And yeah, this is a $4 microcontroller. Selectable bandwidths, there's a squelch for FM. You can zoom the spectrum, change the CW tone, tuning rate, lots more parameters, and there's even more to come because remember, we saved half of the CPU cycle time. So new features, look out. Now, to be honest, you don't get something for nothing, or as Robert Heinlein's acronym puts it, there ain't no such thing as a free lunch. For example, there are out-of-band signals due to the lack of front-end filters. This is not a surprise, and soon we'll have some options to take care of that. Aliases can still sneak through even though we added 30 dB of attenuation. A bit more would be good, but it's certainly manageable and much better than before. If you are so desire, you can use undersampling to actually demodulate the higher order Nyquist zones. I don't think that's a significant source of interference, but sometimes it's just by luck of the draw, you can get third order mixing products sneak up that get through that broad front end and create signals that really aren't there. My Spanmaster did that too, so it's part of the fun of using a minimalist receiver. Sometimes the 256 element filter may not be enough to completely eliminate a very strong opposite sideband signal, but you can be the judge for yourself. I find the receiver to be very usable, even with the filters as is. Now, we intentionally left out that preamp, and when you get to the top half of the HF spectrum, say from 15 to 30 megahertz, where man-made noise is not such a factor, the preamp can be helpful in bringing up some weak signals. On the lower HF bands, you may need to use an attenuator, so our limited A to D resolution could be a factor there. But again, I think it's a very usable receiver, even given the limitations above. Every bit of it which can be addressed with a little bit more cost and additional complexity. All I can say there is stay tuned. In fact, you might ask what's coming up next, because this is a pretty good little receiver. Sure would be cool if it transmitted. Well, it can. As of the most recent iteration of experimental software, the transmitter functionality is now available, and while it's a work in process, it definitely works. What you see is a diagram of a polar transmitter. In the initial release about a year ago, John included concept code for a transmitting device, both using the QSE principle and for polar modulation. Similar to how the Pico Rx works, but in a different way, it uses that unique PIO to generate HF range RF signals. I started experimenting with it last year and made it work. And after playing with the basic HF signal generation capability, John picked up the ball and integrated the full modulator and the rest of the transmit functionality into the receiver in early January 2025. Instead of a quadrature signal, the direct RF waveform is synthesized, starting with a Cortic algorithm that converts the IQ audio picked up by the microphone to amplitude and frequency components. Those signals perform polar modulation of the Class E power amplifier. Now, this is a highly oversimplified translation, but it's an excellent learning opportunity to understand better what I think is going to be the future technology for a lot of ham radio applications. Just a quick walkthrough of that and maybe demystifying it a little bit. When you think about an SSB waveform, it's a signal at RF that contains voice information. It's a form of amplitude modulation, but it's basically a waveform. Well, here are some other waveforms. If you set up an arbitrary function generator with the correct program, it can generate a waveform that looks like a duck. Now, I'm not sure what it would sound like, but the point is, it's just a waveform. So the way John looked at the problem of creating SSB was to sample the input and generate a sequence of waveforms that correspond to the instantaneous phase of the audio signal, and then transforms them to RF through the magic of the PIO, which can generate RF at the high-speed RF rate. The output of a GPIO pin is then used to drive the gate of a Class E MOSFET power amplifier, very similar to those used in lots of other projects, including the Micro SDX. And at the same time, a PWM output voltage is used to change the amplitude of the RF envelope. Polar modulation, amplitude modulated envelope, phase modulated frequency. So we have direct synthesis of the SSB waveform by polar modulation, which I believe aptly deserves the title of a fourth method of single sideband. I did a printed circuit board before I had software to run on it, so I was ready to go when the software became available. I intended it to be an experimental platform, but it hasn't worked out too badly. So the basic components, again, you see the Pico. Now we're talking Pico 2 RP2350 microcontroller. The same RF or OLED display and user interface. We've added an electret mic, the 12-volt power jack now and a regulator, because the transmitter does need 12 volts, and it occupies about maybe 2.5 square inches of real estate right along the top of the board as you look at it. One other piece that's not visible there is the band module. That is a special matching network that's required for each class, for a Class E amplifier for each frequency range. A couple of innovations that I tried to bring to the party. These use magnetic pogo pin connectors, so they just snap in place. And they have a binary coded jumper on the bottom, which tells the Pico which band is plugged in. So there's no need to switch bands. It's simply a matter of dropping the correct matching network in place, and it's ready to go. I also like to heatsink and socket my FET transistors just to make life a little easier if they do get overstressed, and to make it a lot easier if they need to be replaced. A last-minute feature was added, which is an iambic keyer. So while it wasn't wired up at the time the previous picture took, this is the waveform, and it implements the ARRL recommended clear signal initiative 5 millisecond rise time, 3 millisecond fall time. So that is the Pico Rx, and now with TX. The best way to learn more about this project is to go to John Dawson's GitHub page, which you see there at github.com/DawsonJohn. Or from there, you can find the 101 Things, Read the Docs, which has extensive documentation and many links that go to other projects that you might find interesting. And you can find John on YouTube at the 100, if you search for 101 Things. You'll find my exploits at rantechnology.com, and I'll be putting my own code at my GitHub site. So that brings us to the end of the Rx-Tx Pico presentation. But stay tuned, because you never know when something new and cool will drop. For example, just last week, 101 Things released a SSTV, slow scan television decoder using a Pi Pico, and about 5 external parts. So that's going to be of interest to a lot of amateurs, and it's all going to be on the same website. Thanks for watching, and have fun playing with the Pico Rx. 73s from W9RAN.